Hi, this is the Section 5.2 review. What I'm going to do is go over a couple of exponential growth and decay equations, writing the equations, evaluating them, and using the intersection feature on the graphing calculator. And then I'm also going to go through a couple of problems dealing with using a table of values to graph a function that's exponential, and we're going to identify the domain range, the intercepts, the asymptotes, and the intervals of increase or decrease. So starting from the top here, what we're going to do is write a function to represent the population of a city over time, and we're going to use the function then to predict the population of that city after 8 years. So in the problem here it says Westlake has a population of 9,500 people. Its population is increasing at a rate of 2.8%. So we're going to be using a growth equation here since it is increasing, and what that's going to look like is going to be, or we'll just use f of x. We can use f of x equals, and we're going to take our original amount and our population, which is 9,500, and in parentheses, what we're going to do is throw in 1 plus the rate. And we're going to use the rate as a decimal, the 2.8%, so it'll be 0.028, and we are going to raise that to the x power then. I could have also written this as f of t and then put a t up top, but f of x is the same thing. So I'm going to simplify this and say f of x equals 9,500. Again, that's the initial population here. And this will simplify on the inside to 1.028. And we will raise this to the x power. Again, since this base number is greater than 1, that's what means growth. And that's because we're adding the 0.028 to the number 1. This 1 technically means 100%, so you are getting 100% of your population back the next year plus another 2.8%. So the whole inside part is just taking a percent and putting it into a decimal form. Now that we have the equation, we can evaluate after 8 years to figure out what the population will be. So I'm going to evaluate, which means we're going to be substituting a value of 8 in for x. So f of 8 equals 9,500 times 1.028 raised to the 8th power. And then in the calculator, pull this up. In the calculator, you can just throw that all in straight across. And the reason for that is because your calculator is going to do the order of operations, which means that it's going to raise the 1.028 to the 8th power first, and then it's going to multiply it by 9,500. Hit enter, and there's our approximation. So I think about how many full people we have because you can't have 0.64 of a person. So I'm actually going to round this down. So our population is going to be 11,848. And again, the reason I do that is because I consider this how many full people would the model be. And you can't have 0.64 of a person. And we don't technically have 11,849 full people. So I'm going to round down. So it's 11,848. Wait, 848, oops. 848, and that's people. So the population after 8 years will be roughly 11,848. In the next problem, we're going to write a function to represent the population of a city again as a function of time. And this time we're going to use the intersect feature on the graphing calculator to make a prediction of how long it will take for the population to be 8,000 people. So I'm going to be giving a y value here, which is the people amount, and that's the population, and we're going to use that y value to solve backwards for our x value, which will be time in this case. So it says Springfield has a population of 11,500 people, and its population is decreasing at a rate of 1.25%. So that means you're really taking 100% of your population the next year, and you are subtracting 1.25% from it because the population is decreasing. So I'm going to write the equation. We'll do f of x equals, start with the original population, which is 11,500 people, and I'm going to multiply this by 1 minus my rate as a decimal, which is 0.0125, and I'm going to again raise this to the x power. So now let's simplify the inside. So our formula is going to come out to f of x equals 11,500, and then inside the parentheses we'll go to the calculator. And I'm going to take 1 minus, again, we're taking 100% basically, and we're subtracting out the 1.25%, and I just do it all in decimal form. So we end up with 0.9875 as our base number. and that is going to be raised to the x power. So what that really means is after one full year, you will have 98.75% of your population from the year before. And then the year after that, you'll have another 98.75%. So it's always taking a percentage of the year before, and that's why it's exponential. So what we're going to do now is substituting a value of 11,500 in for f of x. So what that really means we would have to do if we were going to solve this using algebra is somehow get x by itself, which you're not going to learn how to do that for a while. So what we're going to do instead is use the graphing calculator. And in the graphing calculator, I'm going to go to y equals, and I'm going to put in first the function up top, the 11,500 times 0.9875 raised to the x power. And in for y2, I'm going to substitute the value of 8,000 people. I'm sorry, it looks like I did make a mistake here. Let's change this. This should have been blah, 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 blah. This should have been 8,000 from the story problem up here. So we're going to predict when the population is going to reach 8,000. I'm sorry, it started off at 11,500. Blah, blah, blah. Sorry if that confused you. Okay, so now in for y2, we're going to substitute the population of 8,000. And I'm going to go to my window. So the x values represent years, so I'm going to go from 0 all the way to like 40 years, and we can count by whatever we'd like. Let's just count by 5s. And the population, I'm going to go from 0 all the way up to a little bit above where it started, and since it started at 11,500, I'm going to go all the way up to 12,000, and we're going to count by thousands. And now I'm going to hit graph, and the first thing we're going to see is this slow curve coming down. And that's going to be the curve representing the population decrease over time. And then I have this line that goes straight across. The y equals 8,000 line is going to intersect at one point. And if we think about that point, the x value of that point is going to represent time, and the y value represent the population. So we really want to find this intersection point because we know that the y value of it is going to be the 8,000, and we need to figure out the x value for time. So I'm going to hit second trace, and we're going to go down to where it says intersect. I'm going to hit enter to select my first curve, enter to select the second curve, and then it wants us to make a guess of where it is approximately, and I'm going to put the cursor over here, and I get 28.85. So in my answer, I'm going to say it will take between 28 and 29 years for the population to be 8,000. Okay, so again, what's different about this problem compared to the last one is this time I'm giving you a y value, and we are working backwards basically to solve for the x value of time. Whereas in the last problem, I was giving an x value of time, and we were solving for a y value of population. And when it's one of those ones, so I'll backtrack real quick. When that was the case, we were evaluating, and we were substituting that value in for x, and we were able to evaluate a function, versus in this one, we would really be substituting the value of 8,000 in for f of x, which is like a y value on the left-hand side. And like I said, we don't know how to solve exponential equations yet, so that's why we had to use the intersection feature. Now what I want to do is complete a bunch of tables. I'm going to do 4 of these. We're going to be just completing a table of values. We'll graph the points, identify the domain, the range, the x-intercept, the y-intercept, the horizontal asymptote, and the interval of increase or decrease. So in this first example, actually all of these problems, I've already crunched out the numbers. So if you have questions on how to put in the calculator, I will go through a couple calculations. So first off, we'll do 4 to the x power. We're going to do 4 to the negative 2. I'll evaluate this first x value of negative 2 just so you can get an idea that it's not going to be a negative number. It comes out to 0.0625. And then what I'm going to do is just fill in the table of values from here. Like I said, I already evaluated all of these by using the graphing calculator. And what you'll notice is that from one value to the next, you're multiplying by 4. And the reason for that is because of this base number. And if we just focus on these values, you can think about it like a geometric sequence with a common ratio of 4, because between terms what we're really doing is multiplying by 4 every time. And if we go back to the equation, that's exactly like what a common ratio did in the Chapter 4 sequence material. So what I'm going to do is plot these points, and I'm going to get really close to the x-axis here. Because notice we're counting by twos, and this first point is at negative 0.0625, so it's really tiny. And then even at negative 1, it's a really tiny point. The y-intercept itself, if you think about it, we're counting by twos on this graph, so your y-intercept is 0, 1. It's only halfway up the y-axis here to that first point. And then when we get to 1, it's at 4. And then when I get to 2, I'm at 16. And again, keep in mind, we're counting by 2, so I'm going to go all the way up here at 216. And I'm going to try to draw on this curve. It's going to be kind of ugly. And it's going to go straight up from there, and I'm going to throw an arrow here and an arrow here. So now that we have the graph, this is an exponential growth function. Our base number is greater than 1. So the values are going to be growing really, really, really fast because they are multiplying by 4 every time. Our domain for all of the functions that we're dealing with in this lesson, domain is going to be all real numbers. And let's look at the range values. All of these range values, no matter what you substitute in for x, all of your range values are going to come out to positive, which means that your y values are all going to be greater than 0. I'll skip down to asymptote first. Notice that even if I put in a value, like if I put in 4 to the negative 10th power, so imagine where negative 10 is on the x-axis. Even if I put in 4 to the negative 10th, it's going to give me this number that says 9.5 blah 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 times 10 to the negative 7th power. Even though you see a negative here, it doesn't actually mean that. What it means is that you would be sliding this decimal over 7 spots. So you would really get 0.000009536. So it's giving you this really, really, really small decimal. But notice that it's not 0, and it's not going to be a negative number. So what that means is that we have an asymptote at y equals 0. Which means that we're never going to cross the x-axis. So you're going to write none for x-intercept. And then think about the y-intercept. Y-intercept is where the x value is 0. So our y-intercept in this case is the point 0, 1. And then where it says interval of increase or decrease, notice that starting from these x values, as our x values move on, and if you're reading the graph from left to right, your x values are going to always be increasing. So we always read left to right, and notice your y values are always going to be increasing in this case. So you're going to say increasing on entire domain. So what that means is as you're moving from left to right on the graph, your y values are increasing. So again, that's an example of an exponential growth function. Now I'm going to do an exponential decay function, which is going to be f of x equals 1/4 to the x power. And again, I'm going to fill in the table of values. Just like I did in the last one, I already crunched these numbers out. And it comes out to something very similar to what we had in the last problem. And the reason for that is in the last problem we had y equals 4 to the x, and in this one it's going to be 1/4 to the x. So it's actually going to be decaying instead of growing. So this graph will probably be as ugly as my last one was. First point is at negative 2 all the way up at 16. And then I have negative 1 is at 4. 0 at 1. And then we're getting really, 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 really close here as we get to the x-axis. And notice what's going to happen is it's going to come from all the way up top, and it's going to start moving its way down, and then we'll start getting closer and closer to this x-axis, but we're never going to touch the x-axis. So again, my domain is going to be all real numbers, which we can use this little notation here. If I make two lines like this and I make an R out of it, that's going to mean all real numbers. My range, again, we're looking at the y values here. Your y values are all above 0, so y is greater than 0. And the reason it's not greater than or equal to is because we cannot actually touch 0. That's the point of having the asymptote of y equals 0, is that it's going to create like a dotted line here, where you're actually going to get closer and closer to this dotted line, but you will never touch the dotted line and you will not cross the dotted line. So that's what an asymptote does. Again, we will not have x-intercepts because you cannot touch that asymptote. The y-intercept in this case is also the point 0, 1. And then notice that our y values are starting to decrease over time. So we would say decreasing on entire domain. Alright, on to the next one. Now this function's a little bit different. We do have a positive value being raised to the x power, but we have a negative number up front that we would be multiplying by. And what's going to happen in this case is we'll still notice the numbers getting larger, except since it's a negative sign, the numbers are going to start getting larger, but in the negative direction, which technically means they're going to be decreasing. So the first number I came out with was negative 1/2, and then I had negative 1, negative 2, negative 4, and negative 8. And again, the reason we can think about these numbers like they're a geometric sequence is because this is an exponential function. So think about what your common ratio would be. If you started multiplying these terms, it looks like you're multiplying by 2 every time. And the reason that is because our base number is 2. Just like in the last problem, or I'm sorry, 2 problems ago, when we had our base number of 4, our y values were multiplying by 4. So it's just like a common ratio. Now I'm going to plot these points. Again, we're counting by 2's, so my first point is going to be at negative 2 and at negative 1/2. Second point is at negative 1, negative 1. Oh, we're not counting by 2's this time, I'm sorry. 0, negative 2 is going to end up being my y-intercept. 1, negative 4 is down here, and 2, negative 8, all the way down here. This graph will look a little bit better than the last one, I think, just because the numbers are spaced out a little bit. And I'm going to throw some arrows on here. And now we'll talk about the domain and range and stuff. So this is a little bit different than the last one. My domain is still going to be all real numbers, but notice our range values are a lot different now. Your y values are all less than 0. And again, they're not going to touch 0 because we'll still have an asymptote there, but the only difference for our range is your sign, your inequality would flip the other way. So it's y is less than 0. We still won't have these x-intercepts because of that asymptote. My y-intercept in this case is where the x value is 0, so my y value is 0 to negative 2. And notice how that relates back to the equation of this first value. That's going to be your y-intercept. Your asymptote will again be at y equals 0, and then notice that the values, again, we're reading the graph left to right, and it looks like your y values keep decreasing over time. So we're going to say decreasing on entire domain. Okay, so this looks kind of like if you were to have a growth function going up this way. This looks like a reflection right over the x-axis. Like if you were to put a mirror where the x-axis is, this looks, if you're following my cursor, it looks like it'd be kind of like a flip right over the x-axis of this, which is what we'll talk about in the later sections. That's going to be called the reflection over the x-axis. So this is a reflection of growth, and then it turns out to actually be decreasing. And then the last case, where we have a number less than 1 for my base number, but I still have this negative multiplier. So I'll fill in the table of values. It's going to look very similar to the last problem, except it's going to be written in reverse order. And the reason for that, again, is instead of having 2 for a base number, I have 1 over 2. So what's going to happen is these values, even though they look like they're getting smaller, technically the numbers are increasing because negative 8 is less than like negative 1. Even though the number 1 itself is less than 8. So that's where it kind of gets a little confusing. I'm going to plot these points. So negative 2, negative 8's down here. Negative 1, negative 4. 0, negative 2. 1, negative 1. And then 2 at negative 0.5. So this one is going to be a reflection of decay, actually. As we make our way over this way, throw the arrows on. So if we think about what a decay function would look like, it's flipping a decay function right over the x-axis. So this is a reflection of decay. The domain of this function, again, it's all real numbers. Your range, we're looking at these y values here. All of them are less than 0. Again, no x-intercepts because we have that horizontal asymptote at y equals 0. The y-intercept, once again, it's where the x value is 0. So at 0, negative 2, which also was this value up front. And then notice your y values are increasing as we move left to right. So we would say increasing on entire domain. And that is basically all of the graphs that we would really see from this section. We were talking about growth, we talked about decay, and then the reflections of growth and decay, and all about the increasing and decreasing.